Welcome to Zanzi Numerics. Today we'll be dealing on, on a challenging problem under vertical projectile motion, which is a hot air balloon or throwing an object from a moving object. Okay, it says that a hot air balloon moves vertically downwards at a constant velocity of 1.5 meters per second. When it reaches a height of 22 meters above the ground, a ball is dropped from the balloon. Refer to the diagram. And then they say that assume that the ball is has the dropping the ball has no effect on the speed of the hot air balloon. Ignore air frictions for the following motion of the ball. So we are told that and when the hot air balloon was moving, and then when it comes to a distance in which the hot air balloon was about 22 meters from the ground, we see that the ball was dropped. And then the other information that we get is that this hot air balloon was moving downwards at a speed of 1.2 meters per second. And then what more information are we given? It's just that information. So we just have to work from that. So let's go to the first question. Question 1. Okay, it says that, no, it's question 9. It was on a previous question paper, it's question 9. Then it says that explain the term projectile motion. So what's a projectile motion? It's an object that has been given initial velocity and moves under the influence of gravitational force only. So we see that we have an object and then we have a gravitational force only. So those are the keywords. It's an object and this object has been given initial velocity. Some say that it's an object that has been given initial velocity and undergoes free fall, because free fall is is the motion in which the only force acting on an object is gravitational. So you can go either way. And then they say that is the hot air balloon a free fall. First we must know that what is free fall. Free fall, it is the motion in which the only force acting on an object is gravitational force only. So let's take the definition and try to apply it to a hot air balloon. Is the only force acting on a hot air balloon if only free fall? For example, if we were to draw a free body diagram of a hot air balloon, will there be the only force of gravity which is going down? No, there will be also the force of the engine, which either pulls the thing up or either pulls it down, which is called Fe, which is the force of the engine applied by the engine. Now, it means that because it is no longer gravitational force, only, it means that it's no longer free fall. It doesn't meet the definition of a projectile. It doesn't meet the definition of an object which is undergoing free fall. So the answer is no. And then when you can give an example that why is it no, you can just say the object is the only force, gravitational force is not the only force. Gravitational force is not the only force acting on the object. And we must know that gravitational force, if it is the only force acting on the object is going to accelerate in the direction of the force according to Newton's second law. So because now this thing is moving at constant velocity, it means that there's no gravitational acceleration there, which tells us that the force are in balance. So you can just say there is no acceleration, because always when there's gravitational force only, the object has to accelerate downwards, which causes the ball to increase speed as it goes down. Because there's only one force which is acting there. But because on the hot air balloon there's another force, which is the force of the engine, it's no longer free fall, no acceleration or constant velocity. So you can use any of these reasons. So now let's go to this one. Let me just clear up some space so that And the following one, which needs more space, we can have the space there. Okay, so it says that calculate the time it takes for the ball to hit the ground after it has been dropped. So what I like to do before doing everything is just to list my variables so that I can know what I have. So the first thing that we have to list, and we must choose direction now. Choose direction. Let's say up is positive, and then let's name our variables. There is initial velocity in which the ball leaves the water balloon with, and we want the time it takes for the ball to hit the ground after it leaves the water balloon and goes down. So this initial velocity, when it comes to water balloon, it is equal to velocity of the balloon, the velocity in which the balloon is moving in, plus the velocity of the ball or of the stone. You can just say velocity of the object. So this is the velocity in which the balloon is moving in, and this is the velocity in which the ball or the object is thrown in. So the velocity in which it will leave the ball will be a resultant vector of those two velocity. So you just have to add and subtract. So we know that if vectors are in the same direction like this, we'll find the resultant like this. But if the vectors, for example, if it was going in the opposite direction, and then we see this one is for the balloon and then this one is for the ball, the resultant will be like this. The resultant will be facing up. So you just find the resultant each and every time that that we see that the ball is thrown, and also there's a velocity of the ball. So now let's see that the ball was thrown in which velocity. So we see that the ball was dropped. So it means that when the person when the ball leaves the thrower's end, there was no velocity put on it, meaning that it is zero. It was just released. But what is the velocity in which the balloon is moving in? The balloon was moving at constant velocity of 1.2 meters per second, and then we must choose direction. If up is positive, down is negative, because now the balloon is going down. It's going to be what? Negative. And then we see that the initial velocity is going to be 1.2 meters per second. So we see that's one will be the answer. And then we go, and then this minus is going to change to the direction now, meters per second, and then the minus will be downwards. So what do we get? We get that here, because now it was not given in initial velocity by the thrower, the velocity that it will leave the hot air balloon, it will be equals to the velocity of the balloon itself, because that's how it works. Imagine, Ori, how does the ball takes the speed of the water balloon? It's like maybe when you are moving in a car, and then when you are moving in the car, and then we see that this is the car, and then the car is going that side. When the car is moving by the speed of 200 kilometers per hour, everything that is inside this car is moving at the speed of 200 kilometers per hour, even you inside that car. But if you press the brake really fast, or maybe if the car hits something, because the body was moving in the speed of 200 kilometers per hour, your body will go forward in that speed. That's why you can hit the dashboard, and that's why there are like airbags in the front, so that you don't need that, and there are also belts for so that you don't go forward. So that's the very similar logistics here. That's it, that now because the balloon is moving downwards with the speed of 1.2 meters per second, it means that everything which is in this balloon, even the ball, is moving at this speed. That's why if you release, this ball will continue going down. So that's what we see. Even it is the same logistics that are there even when you throw a ball. For you to throw a ball in the speed of 2 meters per second, you have to you may have to make sure that your hand is moving at the speed of 2 meters per second. It means that when you throw it, your hand must reach that speed so that everything at the tip of your hand, the way you are throwing, is at 2 meters per second. Your fingertips and also the ball, so that when you release, it continues that very same speed. So it's the very same thing that is in this hot air balloon, to say that everything is moving with this speed, and then when you release, it goes down, and then it continues with this speed. So we say this is the velocity that the ball will leave the hand with. So now when we are still listing our variables, let me just wrap this side so that we can have space. Let me wrap the more professional way. Let me do this, wrap like this. Okay, so now let's list the other variables that we get. The first variable that we listed is the v initial, in which it leaves the hand with it's negative 1.2 meters per second. And then we see another variable, the one that we are given, and it's always this gravitational acceleration, or g, which is 9.8 meters per second squared. Because down up is positive, down is negative, so this one is negative. And also another one is change in y. Change in y, we also have to give it a sign, because the balloon or the distance is being covered going down by the ball which was thrown. It means that it's gonna be negative what, 22 meters. And then what else are we given? We are looking, with this information given, we are looking for the change in time. So let's look for the formula here, in which we can use. So this we are looking for the formula which we can solve for time. Here this time, let's check if other variables we can use to solve the time. Acceleration we have, initial velocity we have, we don't have final velocity. But it means that if we find this final velocity, we can substitute it here and find the time. Is there a formula that we can use to find the final velocity? Here there's final velocity. Here there's this one we have it, this one we have it, and also this is change in y, because now we are dealing with change in y. That's why they wrote it here. So this one we also have it, which is the distance. So we can use this formula, find the final velocity, substitute it here, and then we'll find the time. So let's use that formula. So the first formula we're using is v f squared equals to v initial squared plus 2a change in y, and then we substitute to find the final velocity, and then I say plus or minus. So every time we do an inverse of the square root, is plus or minus. Now let's substitute into this. When we substitute, we are going to substitute the initial, which is negative 1.2 squared plus 2 into negative 9.8, and then what's our change in y? It's negative 22. And then we find our final velocity, which is going to be, and then we got it, which is 20.8. And then after we get it, we have to choose, or there are going to be two answers, positive this or negative this one. But because now up is positive, down is negative, and the final velocity will be going downwards, it's going to be negative. And then this one, and then the negative is going to change to the direction, which is meters per second downwards. And then when we get this, which is our final velocity, we are substituting it here, and then we get the time. So let's substitute. Let's come and write here v f equals to vi plus a change in time. So let's come and substitute. So we substitute everything with this sign. That's very much important. Even the negatives, we substitute them. If we don't substitute them, you'll get the wrong answers. And then we say plus a into negative 9.8, and then change in time. And then we make change in time. Subject to the formula is going to be 20.8 plus 1.2, and then divided by negative. Let me just make space here. Negative 9.8, and then we get our time there. our time to be 2 seconds. So we got our time to be 2 seconds. So we can just come and write here our time to be 2 seconds. So let's see if maybe we can use another way to find the answer. I think that one is the longer way. So let's see if there's another formula we can use. This one we have a change in y, v initial we have change in time we are looking for it, change in time we are looking for it. But here is gonna be a trinomial because change in time squared and then change in time. So it's gonna be a trinomial. But okay, let's wrap this. We got 2 seconds here. And then we come here and wrap. So this one, we just come and write that formula when we are using the way in which it will give us a trinomial, but it will only need one equation or maybe a quadratic equation after. It's a trinomial. Yes, so the distance covered, it was a negative 22 meters going down. I wrap the information here, and then we see the time in which the velocity that it leaves the end with is negative 1.2, and then at the time this one we are looking for it, and then plus half, and then the gravitational acceleration is negative 9.8, and then change in time squared. And then now let's just rearrange everything. We are just writing this one, we are just starting with this one now. So what is half of negative 9.8? Half of half, let me press, it's 9.8, it's 4.9, it's negative 4.9, change in time squared. And then I continue with this one, negative 1.2 change in time, and then plus 22. Now we can see that this is a trinomial now, and then when it is a trinomial now, we just come and use the equation of saying change in time now. Instead of x equals to negative b plus minus a change in time b squared minus 4ac, and then into 2a, then we just come and substitute, in which this one is gonna be our a, this one our b, and then this one is our c. And then we just substitute to say that negative into negative 1.2 plus or minus this, we write b squared. What's our b squared? It's negative 1.2 squared, and then we substitute negative 4. What's our a? Negative 4.9. And then what else do we write? We also write its AC, so our C is plus 22. Sorry. And then we say plus 22. Let me just make more space. There is it. And then we come here. And then after this, we say 2 into the A into negative 4.9. And then we also get our time equals to 2 seconds. So yeah, there it is. Our time is 2 seconds. So now let's go to the second one now. Let's just make space. Let's just make space. Make space, make space, make space. Okay, now let's say when the ball lands on the ground, it is in contact with the ground for 0.3 seconds, and when it bounces vertically upwards with the speed of 15 meters per second, then they say that calculate how high the ball, or calculate how high the balloon is from the ground when the ball reaches its maximum height from the first bounce. So this question is saying that now when this ball which has been thrown, it went and hit the ground, and then when it went and hit the ground, it was in contact with the ground for 0.3 seconds. And then we see that when it hit the ground, it bounces off the ground with what? With this speed. And then the question is, how high was the hot air balloon when the ball reaches its maximum height after the first bounce? So let's just draw the motion here so that let me just cancel here so that I throw it here. So the motion is like this. The ball is thrown, then when the ball is thrown, it goes up. So it is thrown here from 22-meter high place, and then it is in contact with the ground for 0.3 seconds, and then it leaves up with the velocity of what? Of 15 meters per second. 15 meters per second. But here on the final velocity, we had gotten a velocity that is gonna hit the ground here by 20 meters per second. You remember, or we get 20.8 meters per second, and then it got up with this one, which tells us that some velocity was lost here during contact time, maybe to friction, sound, and also other things at the ground when it hits here. That's why it doesn't come back with the same speed, and you realize that the maximum height will continue decreasing until the ball is no longer has kinetic energy because of friction here at the ground during contact time. So that's the information that we are given. And another information which is crucial, they say that when it reaches the maximum height, which is a point here in which what the velocity is 0. Every time at the maximum height, velocity is 0. So what are we called to calculate? See that you must calculate how how high the balloon is from the ground when it reaches its maximum height after the first bounce. So we must check which section of motion we are working on. We are working on this section of motion. We are working on this section of motion. Because if we are working on this section of motion, we can get the time in which it took from here to here, from when the ball reaches, when the ball leaves the ground to when it reaches the maximum height. Because we are looking for the most important thing that can help us to check how high was the hot air balloon, because the movement of the hot air balloon is not tricky, because the hot air balloon is moving at the speed of 1.2 meters per second, is constant. So how do we find the distance of the distance covered by a hot air balloon which is moving at constant velocity? Is very simple, because distance equals to what? Speed times time. Let me say v for speed. So it means that we can just take 1.2 meters and then we multiply it by the time, and then we get this. What does this time represent? They say that how high was the balloon from the ground when the ball reaches its maximum height. So we see that at first it was 22 meters when the ball was thrown. It was 22 meters when the ball was thrown. So we want to see that in that whole movement of the ball until it reaches the maximum height, how far was it now from the ground? Because we hear that we hear that it was moving, so we want to see how far it was moving. So we must just get the time it took from the balloon being from the ball being thrown to the point the balloon from the point the ball reaches the maximum height. We must get the time from here to here, and then when we get the time it takes from the ball being released or dropped to the time in which the ball reaches the maximum height, and then this time it will be the time that the balloon moved from 22 meters above to downwards, and then we will come and substitute this time here, and then when we substitute this time here, we come and find the answer. Whatever answer that we find here is the change in y, is the movement from here to here, and then change in y. What are we looking for? How high is it above the ground? It means we'll just take this change in y, subtract it from here, and we'll get the time here, in which it is the remaining time, it is the remaining distance that the balloon has to move from where it is to reach the ground, because we are not looking for how long did it travel when the ball was moving, but we are looking from how high was it from the ground. So the change in y, which is we are getting here, we'll subtract it from here. So I tried to explain in my best of my abilities, but let's go to the calculation. So now there are sections of time that we have. We have section from time in which it was thrown to here. We calculated it is 2 seconds, and then but section of we have section of that's 2 seconds is from here to here. 0.3 seconds is from here to here is the contact time, and then we are looking for the time here from the time in which it leaves the ground and reach the maximum height. So if we get the time here, we'll just add it with this one, and then it will be our time that the distance that we get when we multiply speed times time, and then we get the time here, and then the speed is already 1.2, then we get the distance. So let's get the time here. So I would like to list my variables first. So the variable first is the initial velocity, in which it leaves the ground with. If up is positive, the ball leaves the ground going up by what? By positive 15 meters per second. But it's not important to write the positive there. And then what's the velocity of final when it reaches the maximum height? The maximum height, always the velocity is 0. And then what else do we know? We always know what? 9.8, which is our gravitational acceleration. Because it's always downwards, it's going to be 9.8 meters per second squared. And then now we're going to use this to find what? To find the time. Let's see if there's an equation that we can use. Let me just rub here so that we can see our equations properly. Okay, so we are looking for the equation that has the what? The time. So this one we have, this one we have, this one we have. So we can just substitute that one. V final equals to V initial plus A change in time, and then we come and substitute what is our V final 0. V initial is 15 plus acceleration negative 9.8. What is our change in time there? Our change in time is gonna be change in time equals to negative 15 over negative 9.8, and then we are gonna get our change in time as, and then it's 1.53 seconds. And then when we get our change in time now, it's our change in time for this section of motion, which is what? Which is 1.53. Now we have to add these 3 changes of time so that we can get the total time the ball was moving until it reaches the maximum height. And then we get that is to change in time equals to 2 plus 0.3 plus 1.53, and then we get 3.83 seconds. So this is the total time it take, and then we come and just multiply this distance times time is equals to 3.83. So 1.2 times 3.83, and then we get that the distance it had moved 4.956 meters. So we just come and check or no. Okay, let me rub here so that we can just see what you're talking about. So now all that time it had moved downwards by 4.5. So we are looking for the remaining here. So we just say this minus this. We just say 22. Our change in y is gonna be 22 minus 4.596, and then it's gonna be let's round it to 17.4 meters. That's the height above the ground. So here it's gonna be 17.4, then that's the height, so 17.4. So that's how we get. But if you're not comfortable with this one, after you get this one, you can just use equations of motion to get the answer. You can just use one of these equations. Let me check which equation apply. So let's check the variables that we have. We have a time here, and then when we have time, we also have distance, and then we also have a velocity, which is the initial velocity. So, or it is that it is the general velocity in which the ball was traveling in. So we can just use this formula and come and say change in y equals to v initial change in time plus half change in time squared. So this formula is the same as this one. I will show you how it is the same. It's because this formula, you just come and say change in y, which represents the distance, equals to v change in time, and then it's going to be plus half into 0 change in time squared, because there is no acceleration here. This thing is moving at constant velocity. So because there is no acceleration, it's going to be change in y equals to v initial change in time, which is similar to this, because d is the same change in y, and then velocity is the same with velocity, and then change in time is the same as change in time. So you just come and substitute this, and get the same answer. So this is how we do this problem. Be sure to like, follow, and subscribe, and then we'll deal with more problems. And also, there's other videos. I did a playlist on different problem types of vertical projectile motion. I will post some of the link in the description. See you.